Welcome, my dear listener. Close your eyes, slow your breathing, and let's drift into a question that has puzzled philosophers and scientists for centuries. Time, it rules our lives. It tells us when to wake, when to eat, when to work, and when to rest. But beyond human schedules, beyond the ticking of seconds, minutes, and hours, what is time to the universe itself? Does it flow like a river, carrying us forward? Or is it simply an illusion, stitched together by memory and anticipation? Tonight, we will journey through the cosmic puzzle of time, gently, as if following the stars across a silent night sky. From the moment we are born, our lives are cradled by the rhythm of time. Even before we can read numbers on a clock, we feel its gentle presence. A baby learns hunger in cycles, sleeping and waking in natural rhythms, guided not by minutes or hours, but by the body's own hidden clock. As we grow older, those rhythms become structured by the world around us. The rising and setting of the sun, the changing of the seasons, the rhythm of day and night, all of these patterns whisper to us that something greater is moving, and that we too must move within it. This is where our relationship with time begins, not as a number, but as a feeling, a flow, a pulse woven into the fabric of existence. Imagine for a moment the earliest humans looking up at the sky. With no clocks, no calendars, they would have seen time revealed in the great cycles of nature, the moon waxing and waning, marking months, the sun climbing higher in the sky during summer and dipping lower in winter, shaping seasons. The migration of animals, the blooming and falling of leaves, the tides rolling with the pull of the moon was a reminder that life is not static, but endlessly changing. These changes became humanity's first awareness of time. It was not measured in hours or minutes, but in harvests, in cycles of light and darkness, in birth and death. Over thousands of years, as civilizations grew, so too did the need to measure time more precisely. Farmers needed to know when to plant and when to harvest. Builders of temples and pyramids wanted to align their monuments with the heavens. Priests and astronomers gazed at the stars, mapping their patterns to predict the future. Out of this deep longing for order, the first calendars were born. Ancient Egyptians built obelisks that cast shadows to mark the hours of the day. The Babylonians divided the circle into 360 degrees, giving us the structure that would later become the basis for minutes and seconds. The Mayans and Chinese crafted calendars so intricate they could track the rhythms of the cosmos for centuries ahead. Humanity's fascination with time grew alongside its awareness that life itself was fleeting, and that to understand time was, in a way, to wrestle with mortality. But even as we developed instruments to measure time, our bodies never stopped keeping their own natural rhythm. Inside us lies what scientists call the circadian clock. It is not made of gears or springs, but of biology molecules in our cells that rise and fall in predictable cycles, guided largely by light. When sunlight touches our eyes in the morning, signals travel deep into the brain, telling our bodies to wake, to release hormones that energize us, to set our internal day in motion. As darkness falls, the brain releases melatonin, signaling it is time to rest. Without even glancing at a clock, our bodies know when it is day and when it is night. Even animals and plants live by these internal rhythms. Flowers open with the dawn and close with the dusk. Birds begin their songs at first light. Every living thing carries a sense of time, encoded not in numbers but in biology. Yet, our perception of time is far more fluid than the precise ticking of a clock. Think of how quickly an hour can vanish when we are lost in joy, immersed in a conversation, or caught in the beauty of music. Now, think of how slowly minutes drag when we are anxious, waiting for news, or staring at a ceiling in sleepless hours of the night. To the clock, both experiences last the same 60 minutes, but to the human mind, one feels fleeting and the other eternal. This tells us something remarkable, that time, as we live it, is not just physical but psychological. It bends and stretches, expands and contracts, depending on the state of our awareness. Children often live with the sense that time is endless. Summers seem infinite, and a year feels like a vast ocean of days. But as we grow older, years slip past with increasing speed. A single decade can feel shorter than a childhood summer once did. Scientists suggest this might be because as we age, each new year becomes a smaller fraction of our total life lived. A year to a 5-year-old is a fifth of their entire memory, but to a 50-year-old, it is only a 50th. In this way, time feels faster not because clocks change, but because our perspective does. Clocks and calendars impose structure, yet our sense of time is deeply personal, shaped by memory and emotion. We remember moments of joy as bright flashes, timeless in their intensity. We recall grief as a stretch of endless days, heavy and slow. Even anticipation plays tricks on us. Waiting for something we desire makes the minutes expand, while surprise events collapse time into a blink. The brain, in weaving memory and expectation, gives us the feeling of time flowing, but that flow is far less steady than we imagine. As societies advanced, time was harnessed not only for survival, but for control. The Industrial Revolution turned time into a currency. Factory bells dictated when workers should arrive, eat, and leave. Railroads demanded standardized time zones so trains would not collide. In the modern world, time became measured, managed, and sold, down to the second. We invented atomic clocks that measure time with breathtaking precision, clocks so exact they would lose less than a second in billions of years. We synchronized satellites, guided airplanes, and connected the internet, all on the strength of exact timekeeping. Yet, the more precise we became, the further we drifted from the natural rhythms of body and earth. Many of us live by alarms, deadlines, and schedules rather than the rising of the sun or the rhythm of our own breath. And still, despite all of this measurement, time remains elusive. We live by it, we fear it, we cherish it, but when asked to define what it truly is, we stumble. Is time a thing that exists outside us, ticking relentlessly in the universe? Or is it something woven into our perception, a tool our minds use to make sense of change? The human sense of time is caught between these two poles, the measurable precision of science and the fluid subjectivity of experience. When you close your eyes and let the moments pass, you can feel this duality. Your heartbeat is steady, marking its own rhythm. Your breath rises and falls like a tide. Around you, the world moves forward, but within you, the experience of time is uniquely your own. And perhaps that is the mystery. Our clocks divide days into hours and hours into minutes, but life itself unfolds in moments, and moments do not always obey the same rules as numbers on a dial. When we think about time as a concept, it often feels like something solid, something that moves forward no matter what we do. This picture of time as an ever-flowing river has shaped human imagination for centuries, but perhaps no one gave it a more lasting scientific voice than Sir Isaac Newton. To Newton, time was not just a tool for humans to measure their days or track the motion of the stars. He saw time as something deeper, something woven into the very fabric of the universe itself. He called it absolute time, a grand, universal clock ticking silently in the background of reality. Always steady. Always the same for everyone, everywhere. In Newton's era, the late 1600s, science was entering a golden age. Galileo had already shown that the heavens obeyed laws of motion rather than mystical forces. The telescope had revealed moons orbiting Jupiter and the rugged craters of Earth's own moon. The world was beginning to look less like an unpredictable mystery and more like a machine, precise, predictable, elegant in its design. Newton was at the heart of this revolution. With his laws of motion and universal gravitation, he gave humanity the power to describe how objects move not only on Earth, but across the cosmos. Yet for those laws to make sense, he needed a stage on which everything played out, a foundation of certainty. That foundation, for Newton, was absolute space and absolute time. To Newton, absolute time was like an invisible heartbeat of the universe. It was not dependent on human clocks or earthly rhythms. Whether a planet was spinning around a star or a pebble was falling to the ground, these events unfolded against the backdrop of a universal ticking Time flowed uniformly, independent of motion, unaffected by matter, untouched by human perception. If two people were separated by oceans, if one was in darkness and the other in daylight, Newton believed they were still moving through the same stream of time together, second by second, heartbeat by heartbeat. This view of time was comforting. In its certainty, it suggested that the universe was orderly, that there was a master clock keeping track of everything, and that no matter where you were, you could imagine time as the same steady rhythm ticking away in the background. It aligned with the intuition most of us carry even today, the feeling that time simply is, that it flows whether we notice it or not. To Newton, it was as real as the force of gravity or the solidity of a rock. He once wrote that, absolute, true, and mathematical time, of itself, and from its own nature, flows equably without relation to anything external. In his mind, time did not need the world to exist. It existed independently, carrying the world along with it. But how did people in Newton's time experience and measure this idea of absolute time? They had pendulum clocks, sundials, and early mechanical devices, none of which could rival the precision of our modern atomic clocks. And yet, these instruments were enough to reinforce the idea that there was a steady, objective rhythm to reality. A pendulum swung with regular motion, and the gears of a clock moved predictably. This mechanical regularity seemed to mirror the deep truth Newton believed in. Clocks became symbols of the universe itself, orderly, predictable, ticking in perfect unison with the invisible rhythm of absolute time. Imagine a craftsman in Newton's England winding a clock each morning, trusting that its ticking matched something greater, something beyond human design. Every tick of the pendulum, every movement of the gear, was a reflection of that hidden, universal order. Even if the clock was imperfect, the assumption was that perfection existed somewhere, in the invisible backdrop of time itself. That was Newton's vision. Clocks did not create time, they only tried to keep pace with the universal clock already ticking behind reality. Philosophically, this view also made sense to many. If time was absolute, then past, present, and future were objective facts, not dependent on perception. The past had already happened, the present was unfolding, and the future awaited, all marching along the same unbending river. This provided not just scientific clarity, but also a sense of comfort to human beings grappling with their place in the cosmos. It meant that there was a universal now that every creature and every star shared together. Even if you could not see the far side of the universe, it was unfolding in sync with you. Newton's absolute time also solved practical problems. His equations of motion relied on it. To calculate how planets moved around the sun, or how a cannonball arced through the air, he needed a measure of duration that was consistent everywhere. Without such a foundation, the mathematics of motion would collapse. For Newton, then, absolute time was not just a philosophical idea, but a necessary element of science itself. It was the silent metronome keeping the universe in step. And yet, even in Newton's time, some thinkers were uneasy with this concept. The philosopher Gottfried Wilhelm Leibniz argued that time might not exist independently at all, but rather only as a relation between events. For Leibniz, if nothing happened, no motion, no change, then time would be meaningless. Newton, however, disagreed strongly. He imagined that even if the universe were empty, even if no stars or planets moved, absolute time would still tick away, unseen and eternal. This debate between Newton and Leibniz marked one of the earliest clashes over the true nature of time, a clash that still echoes in physics today. To bring Newton's view into a more human frame, imagine you are standing in a quiet meadow. Clouds drift slowly across the sky, and you feel the wind shift. In Newton's picture, whether you watch the clouds or not, whether you breathe deeply or hold your breath, time continues to move forward beneath it all, steady and indifferent. It does not wait for you, and it does not depend on your noticing it. It is like a river flowing beneath the ground, carrying everything with it even when unseen. This is the essence of Newton's absolute time, constant, invisible, impartial. What makes Newton's view so powerful is how natural it feels. Even today, most of us live as though absolute time exists. When we make appointments, set alarms, or synchronize watches, we assume that time is the same for everyone, everywhere. We take it for granted that 1 second in your life is the same as 1 second in mine, and that clocks merely reveal what is already there. This everyday experience of time is a direct inheritance from Newton's vision. For centuries, his picture was not only scientifically useful but philosophically satisfying. It gave us a stage on which to build the modern world. But what is striking, when we reflect gently, is how much of this idea rests on intuition and trust. We cannot see absolute time. We cannot hear it or touch it. We experience moments, we measure intervals, but the steady flow Newton described remains invisible. It exists as a background assumption, something we believe in to make sense of change and motion. And though Newton built a framework of breathtaking success, this absolute time, so deeply embedded in his vision of the universe, would one day be challenged in ways he could scarcely imagine. For more than 2 centuries after Newton, the idea of absolute time stood unchallenged, like a cornerstone of the scientific world. Philosophers questioned it, but no one could deny its usefulness. The planets circled the sun just as Newton's laws described, and the mechanics of motion seemed to fit perfectly with the notion of a universal clock ticking evenly everywhere. To many, it felt as though the debate over time had been settled forever. But in the early 20th century, a young man working in a Swiss patent office would unravel this comforting picture. His name was Albert Einstein, and with his theories of relativity, he would reveal that time was not absolute at all. Instead, it was flexible, malleable, and intimately tied to space itself. Einstein's revolution began with a simple, almost childlike curiosity. What would it be like to chase a beam of light? As a teenager, he imagined running alongside it, trying to catch up. This playful thought experiment planted the seed of a profound realization. The speed of light, as described by James Clerk Maxwell's equations of electromagnetism, seemed to be a constant. No matter how fast you moved, light itself always raced away from you at the same speed. This puzzled Einstein deeply, because according to Newton's framework, speeds should add together. If you were on a moving train and threw a ball forward, someone standing on the ground would see the ball moving faster than you did. But if you replaced the ball with light, the math no longer worked. The speed of light was stubbornly unchanging, no matter the observer. Einstein's insight was to accept this strange fact and see where it led. If the speed of light is constant for everyone, then it is not speed that changes but time and space themselves. In other words, the universe bends its rules so that light never has to. This single shift in perspective cracked open Newton's vision of absolute time. Suddenly, time was no longer a universal flow that ticked the same everywhere. Instead, it became relative, tied to the motion of the observer. The implications were extraordinary. Imagine 2 people, one standing still on Earth, and the other traveling near the speed of light in a spaceship. To the person on Earth, time moves along at its usual pace, but to the traveler, time slows down. Their heart beats more slowly, their thoughts move at a different rhythm, and their clock ticks more gently. When the traveler eventually returns, they will have aged less than the person who stayed behind. This effect is known as time dilation, and though it sounds like science fiction, it is a measurable, proven fact. One of the first demonstrations of this came not from spaceships but from subatomic particles called muons. These particles are created when cosmic rays strike Earth's atmosphere, and they decay very quickly, usually within microseconds. According to Newton's framework, very few of them should reach Earth's surface because their lives are so short. Yet in reality, far more muons survive the journey than expected. Why? Because they are moving close to the speed of light, and from their perspective, time itself is slowed. In their stretched-out experience of time, they live long enough to reach the ground. This was Einstein's revolution. Time is not absolute, but relative. It depends on motion and speed. A second for one observer may not be the same as a second for another. This shattered the idea of a single cosmic clock. Instead of one steady beat governing the universe, each observer carried their own rhythm of time, all equally valid. The universe, it seemed, did not know one time but many, and Einstein did not stop there. In his general theory of relativity, he extended this idea further, linking time not only to speed but to gravity. He showed that massive objects like stars and planets bend the fabric of space-time, creating what we feel as gravity. In this warped fabric, time itself is stretched and slowed. A clock placed on the surface of Earth ticks more slowly than one in the emptiness of space. A clock orbiting near a black hole, where gravity is unimaginably strong, ticks more slowly still. Time, then, was not a universal flow at all. It was something flexible, woven into the very structure of reality, bending and stretching with mass and motion. This was an astonishing shift in human understanding. Newton's universe was like a stage on which events unfolded against the steady background of absolute time. Einstein's universe had no such stage. Time itself was part of the play, reshaped by the actors, bending with the movements of matter and energy. The old certainty of a universal now melted away. In its place came a vision of a universe where different observers live in different times, all equally real, all equally true. Think for a moment about what this means for our daily lives. The satellites that guide your phone's GPS are orbiting high above Earth, where gravity is weaker and their speed is high. Because of relativity, their clocks tick slightly differently from clocks on the ground. Without correcting for these tiny distortions in time, your GPS would drift off by kilometers each day. Einstein's theory is not only a philosophical revolution, but a practical necessity for modern technology. We live in a world where relativity quietly guides us, even if we rarely notice it. Yet beyond technology, Einstein's view carries a deeper, almost poetic consequence. If time is relative, then the idea of a single, universal present dissolves. The moment you are experiencing right now may not be the same moment for someone far across the cosmos. Two events that seem simultaneous to you may not be simultaneous to someone moving at a different speed. The present, then, is not universal but personal, tied to perspective. This challenges our very sense of reality. What we call now is not shared across the universe but stitched together by our own motion and position in spacetime. Einstein himself once remarked that the distinction between past, present, and future is only a stubbornly persistent illusion. In his equations, time does not flow as we feel it does. Instead, the universe can be described as a four-dimensional fabric of spacetime, where all events past, present, and future coexist. To us, living beings who remember the past and anticipate the future, time feels like a river flowing forward. But to the universe, time may simply be another dimension, like length or width, already laid out in its entirety. This idea is deeply unsettling and yet profoundly beautiful. It suggests that time is not a single thread unraveling, but a vast tapestry in which every moment exists eternally. Your birth, your present heartbeat, and your far-off future are all threads woven into the same fabric. You experience them in sequence, one after another, but the universe may hold them all at once. In this view, the flow of time is not an absolute truth, but a perspective shaped by consciousness and motion. Einstein's revolution did not erase Newton's vision, but revealed its limits. Newton's laws still work beautifully for everyday life: falling apples, moving cars, circling planets. But when the speeds approach that of light or the gravitational fields grow immense, Newton's absolute time gives way to Einstein's relative time. What we once believed to be solid and universal is now flexible, personal, and astonishingly complex. When Einstein proposed his theory of relativity, he did more than just change the way we think about clocks, motion, and gravity. He fused together two concepts that had long been considered separate: time and space. Before Einstein, most people thought of space as the stage on which the universe unfolded, an infinite backdrop that held stars, planets, and galaxies. Time, on the other hand, was imagined as the steady flow that carried events from the past into the present and then into the future. They were two different things, one describing where, the other describing when. But Einstein showed that this separation was an illusion. In reality, time and space are not two different fabrics, but a single fabric woven together into what we now call spacetime. To grasp this idea, imagine that you are floating in a vast, endless void. No stars, no planets, nothing around you, but emptiness. In Newton's vision, you would still exist within space, and time would still pass, ticking away independently of your surroundings. Space would be the stage, and time would be the clock. But in Einstein's vision, you are not in two different realms, space here, and time there. You are within one continuous reality. Your position is not only about where you are in space, but also about when you are in time. You are not just at a location, you are at an event, and every event is defined by 4 coordinates, 3 for space and 1 for time. This fusion of space and time into a single entity reshaped the way scientists understood the universe. If you picture space as a 3-dimensional grid, Einstein added time as a 4th dimension, creating a kind of cosmic stage that is not static, but dynamic. Events in the universe are not just points in space, but points in spacetime, connected by the geometry of this 4-dimensional fabric. Your birth, your first step, your heartbeat in this moment, all are coordinates in spacetime. They exist as part of the structure, not floating independently, but woven into the tapestry of the cosmos. To help us visualize this, physicists often use the metaphor of a rubber sheet. Imagine stretching a large sheet taut and placing a heavy ball in the center. The ball creates a depression, warping the sheet around it. Now, if you roll a smaller ball nearby, it will curve inward, pulled not by an invisible force, but by the bending of the sheet itself. This is how Einstein redefined gravity, not as a mysterious force acting at a distance, as Newton described, but as the result of spacetime being curved by mass and energy. Planets orbit stars not because they are tugged invisibly, but because the star bends the fabric of spacetime, and the planets follow the curves of that geometry. In this view, time itself is caught in the fabric. Place a clock closer to a massive object like a planet or a star, and spacetime around it bends more strongly. That bending stretches time, causing it to pass more slowly relative to a clock farther away. This phenomenon is called gravitational time dilation, and it is not just a theoretical curiosity. It has been measured in laboratories on Earth by placing clocks at different heights, one near the ground and another a few meters higher. The clock closer to Earth's surface, where gravity is slightly stronger, ticks more slowly than the one above it. The difference is tiny but real, and when magnified near extreme objects like black holes, it becomes dramatic. Near the edge of a black hole, time slows so intensely that an outside observer could watch a clock tick almost to a halt, while for someone near the black hole, life would feel normal. This shows us that time and space cannot be untangled. The bending of one affects the other, and both together form the stage on which the universe exists. A traveler moving at great speeds does not just move through space differently, they also move through time differently. A star bending space with its gravity is also stretching time. Space and time are inseparable threads of the same cloth, woven together so tightly that to speak of one without the other misses the essence of reality. One of the most profound consequences of this realization is the way it changes our idea of the universe itself. If spacetime is a fabric, then the cosmos is not just a collection of objects drifting in emptiness, but a structure with shape and texture. Galaxies, stars, planets, and even light itself move along the curves of this fabric, guided not by invisible forces, but by the geometry of spacetime. In this picture, the universe is not static or mechanical, but dynamic and alive. A great cosmic fabric that bends, stretches, and evolves with the matter and energy it contains. For us, this has practical consequences that reach into daily life. The global positioning system, the network of satellites circling Earth that guides your phone and car, must account for both special relativity and general relativity, the slowing of time due to speed and the bending of time due to gravity. Without these corrections, GPS would become useless within hours, drifting miles away from accurate positions. Each time you navigate to a destination, you are unconsciously relying on the reality of spacetime, on Einstein's fusion of time and space into a single fabric. Yet beyond the practical lies the philosophical. If space-time is a fabric, and all events are coordinates upon it, then what does this mean for our experience of time as something that flows? When you look back at your childhood, those moments are not gone in the language of space-time, they are still there, embedded in the fabric, like fixed points on a map. When you imagine your future, those events too exist in space-time, though you have not yet reached them. The universe does not distinguish between past, present, and future in the way your consciousness does. To the fabric of space-time, all events simply are, arranged in a vast four-dimensional structure. This perspective challenges the way we think about our own lives. We are used to imagining time as a river, flowing from the past into the future, carrying us along. But Einstein's spacetime suggests that the river is more like a landscape, already laid out, with every bend and twist existing simultaneously. We move through it, perceiving the journey as a flow, but in reality, all points in the journey may coexist in the grand fabric. Your first breath, this very moment, and your last heartbeat may all be stitched into the same cosmic quilt, equally real, equally part of the universe's structure. Of course, our minds resist this idea. We feel the flow of time as something deeply real, something that separates what has been from what is to come. Memory anchors us in the past, and anticipation pulls us toward the future. But in Einstein's universe, that sense of flow might be an artifact of consciousness, a way our minds interpret the path through space-time. The fabric itself does not flow. It simply exists, stretched and curved, holding within it all the events of reality. To imagine this is to confront one of the deepest mysteries of existence. If time and space are one fabric, then the universe is not simply a stage for our lives, but a structure in which our lives are threads. Every action, every choice, every heartbeat is a point woven into space-time. The stars do not merely shine in the night sky, they bend the fabric around them, shaping the rhythm of time itself. And we too, with our tiny mass and fleeting lives, are part of that fabric, moving along its curves, carried within its weave, inseparable from the cosmos that holds us. If there is one aspect of time that feels most undeniable to us, it is the present. Right now, this very moment, the words you are hearing, the sound of your breath, the rhythm of your heartbeat, all of these form what we call the present. We live our lives in it. We remember the past. We anticipate the future, but we only ever exist, it seems, in the now. The present feels alive in a way that the past and future do not. And yet, when physics tries to describe the universe, the concept of the present becomes strangely difficult to define. It slips away like mist in your fingers. This tension between the way we experience time and the way the universe describes, it is what philosophers and scientists call the problem of the present. To understand this problem helps to imagine how physics views reality. In Newton's world, time flowed like a river, steady and absolute, carrying the present forward with it. Everyone, everywhere, would agree on what now was. In Einstein's world of relativity, that certainty was broken. The idea of a universal now dissolved. If you and I are standing still together, we can agree on what is happening at this moment. But if one of us begins to move very fast, approaching the speed of light, our sense of what counts as the present will no longer match. Events that are simultaneous for you may not be simultaneous for me. Relativity teaches us that the present is not universal, but depends on the observer. The concept of now becomes relative, stretching and shifting across space-time. This leads to a strange and unsettling realization. If the present depends on perspective, then it cannot be a fundamental feature of reality. It is not written into the equations of physics. Instead, what physics gives us is a picture of space-time as a whole, a vast four-dimensional fabric where past, present, and future coexist. Every event, your birth, this moment, your far-off future, exists somewhere in the fabric. From this view, the universe is like a map. All the cities and roads exist on the map at once, but you experience the journey by moving through them. The present, then, is not a universal truth, but a feature of our movement through the map of spacetime. And yet, for us, the present feels undeniably real. When you close your eyes, you are not in the past or future, but here now. The memory of yesterday is something you recall, not something you live. The anticipation of tomorrow is a thought, not an experience. But this very moment, this heartbeat, this breath, that is where life happens. Our consciousness seems to carve the present out of the fabric of spacetime, elevating one thin slice of it and declaring it real. Why should that be so? Why does physics treat all of spacetime as equally valid, while we experience only the shimmering edge of the present? Philosophers have struggled with this for centuries. Some argue that the present is an illusion, a trick of the mind. In this view, the brain stitches together sensory input and memory into a seamless experience of now, but the underlying reality has no such privilege for the present. Others argue that the present must be real, that the universe cannot just be a frozen block of spacetime, because the flow of time feels too immediate, too undeniable, to be dismissed as illusion. If the present is real, then perhaps our physics is incomplete, missing some deeper element that accounts for the vividness of now. Consider what it feels like to watch a movie. A film reel is made of individual frames, each a frozen image, laid out on a table. All the frames exist simultaneously. Nothing moves. But when the frames are played in sequence, projected at speed, we see motion. Characters run, speak, and live. Some philosophers suggest that reality may be like this. The universe is a collection of events laid out in spacetime, all existing at once, but our consciousness moves through them in sequence, creating the illusion of flow. If so, the present is not an objective property of the universe, but a feature of our perception. Neuroscience offers a fascinating perspective here. The brain does not experience events instantaneously. When light hits your eyes, it takes milliseconds for the signal to travel to your brain, be processed, and become an image. When sound enters your ears, it too takes time to be processed into meaning. Even the sensation of touch is delayed by the time it takes nerves to send signals. This means that your experience of the present is always slightly behind reality. The now you feel is a reconstruction, built by the brain from inputs that are already in the past. To make sense of this, the brain integrates these signals into a coherent moment, smoothing them into a seamless present. In this way, the present may be less like an objective slice of time and more like a story the brain tells itself. And yet, even if the present is a construction, it is the construction that gives us our sense of reality. Without it, life would dissolve into chaos. Imagine if you perceived every signal at the moment it arrived, sight delayed by milliseconds, sound arriving at a slightly different time, touch lagging behind them both. Reality would feel fractured. Instead, your brain synchronizes these inputs, creating a unified now. This present may not exist in the equations of physics, but it exists for you, as the arena in which experience unfolds. The problem of the present, then, is not just a question for physics, but for consciousness. Perhaps physics is correct in saying that past, present, and future all coexist in spacetime. But perhaps it is also correct to say that for a conscious being, the present is uniquely real, because consciousness itself is the process of moving through spacetime moment by moment. To live is to experience the present. To be conscious is to know now. This tension between the universe's indifference to the present and our insistence on it reveals something profound. The cosmos may not know what time it is, but we do. Our experience of now may be the way the universe comes to know itself, one heartbeat at a time. When you sit quietly and breathe, when you notice the warmth of sunlight or the sound of rain, you are touching the present in a way no equation can capture. It may be fleeting, it may be fragile, but it is also the only reality we ever truly inhabit. When you look around at the world, you can sense something very simple yet deeply profound. Time moves in one direction. You wake up, the day unfolds. The sun sets, and night arrives. A candle burns down to wax. A leaf falls from a tree and crumbles. Smoke rises into the air and never returns to the flame. We never see these processes reverse. You do not see broken glass leap from the floor and reassemble itself on a table. You do not see waves retreat into the ocean and form back into a towering crest before they crash again. Time, as we experience it, always has a direction, always points forward. This flow from past to future is what physicists call the arrow of time. It may sound obvious, but when you step into the realm of physics, the arrow of time becomes something of a mystery. The equations that describe the laws of motion, from Newton to Einstein, do not actually care about direction. They work just as well if you imagine time running backwards. If you take a simple physical process and reverse it mathematically, the equations hold true. If a ball rolls forward across the floor, the equations are just as valid if you imagine the ball rolling backward. This symmetry of time in physics is strange because it does not match the reality of our lives. We do not experience a symmetrical time. We experience time that moves in one way only, from what we call the past into what we call the future. Why should this be so? One of the deepest insights into this mystery comes from the concept of entropy. Entropy is a measure of disorder, a way of describing how organized or disorganized a system is. Think of a deck of cards freshly arranged. In order, it is highly organized, low in entropy. Now shuffle that deck. With each shuffle, the cards become more mixed, more disordered, higher in entropy. The second law of thermodynamics tells us that in a closed system, entropy always increases over time. In other words, the universe moves from order to disorder, from low entropy to high entropy. This law gives us a natural arrow of time. The direction of time is the direction in which entropy increases. Consider again the broken glass. Before it shatters, the glass is whole, its pieces neatly arranged into a single, ordered shape. When it falls and breaks, the pieces scatter into disorder. The entropy has increased. It is possible, in theory, for the pieces to come together again, but the odds are so astronomically small that it never happens. This is why we never see time reverse in daily life. Entropy ensures that processes unfold in one direction. Eggs break, candles melt, stars burn out. These are the marks of the arrow of time. This arrow also explains something as familiar as memory. We remember the past, but not the future. You know what you ate for breakfast yesterday, but you do not know what you will eat tomorrow. Why should memory work this way? Because the past is in a state of lower entropy compared to the present. The universe leaves traces as it evolves. A footprint in the sand tells you that someone walked there before. Smoke in the air tells you that a fire once burned. These traces exist because entropy increases, and as it does, it leaves behind records. The future, by contrast, has not yet unfolded into higher entropy, so it leaves no traces for us to perceive. Memory itself is a consequence of the arrow of time, but this raises another question. Why does entropy increase at all? Why does the universe have this tendency toward disorder? One answer lies in the beginning. The universe, at the moment of the Big Bang, appears to have been in a state of extraordinarily low entropy. It was ordered in a way that almost defies comprehension, smooth and uniform, yet containing the seeds of galaxies and stars to come. From that improbable beginning, entropy has been increasing ever since, giving rise to the arrow of time we experience. If the universe had begun in a state of high entropy, everything would already be maximally disordered, and there would be no sense of time flowing forward. The arrow of time then may be rooted in the extraordinary initial conditions of the cosmos itself, yet the mystery is far from solved. Physicists still debate why the early universe was so low in entropy. Some suggest it is simply the way things began, brute fact with no deeper explanation. Others propose that the universe we see is only one part of a larger multiverse, and that the arrow of time we experience is a local feature, not a universal rule. Still, others wonder whether entropy and time are not fundamental at all, but emergent properties, arising from something deeper we do not yet understand. The arrow of time also takes on strange forms when we look at the universe on the largest and smallest scales. At the level of quantum physics, the laws seem to be even more indifferent to time's direction than at the level of everyday motion. A particle can move forward or backward in time according to the equations, and some interpretations even suggest that particles do both at once. At the cosmic scale, black holes present another puzzle. When matter falls into a black hole, its information seems to vanish, swallowed by the event horizon. This process appears to erase order and increase entropy dramatically, further anchoring the arrow of time. And yet, physicists are still grappling with whether the information is truly lost or encoded in some hidden way on the surface of the black hole. For us, living in the middle ground between quantum scales and cosmic horizons, the arrow of time is most visible in our everyday experience. It is in the aging of the body, the decay of memories, the flow of experiences that carry us forward. You can feel it in the way moments pass and cannot be retrieved. You can feel it in the way history piles behind us, irretrievable, while the future stretches ahead as mystery. The arrow of time gives our lives shape and meaning. Without it, there would be no stories, no growth, no anticipation. There would only be a frozen block of space-time with no sense of before or after. And yet, when we reflect deeply, we realize that the arrow of time may not be as fundamental as it feels. The laws of physics allow for reversals, for symmetries, for timelessness. The flow we experience may be a feature of entropy, of the way the universe began, or even of the way consciousness stitches reality together. Still, for us, the arrow of time is inescapable. It is the invisible hand guiding us from one heartbeat to the next, the silent current carrying us from birth toward death, the unbroken line along which our lives unfold. When we turn our attention from the grand cosmic scales of stars, galaxies, and entropy, and instead focus on the smallest building blocks of reality, the question of time becomes even stranger. Quantum physics, the science of the subatomic world, has given us the most accurate predictions in all of science. It describes the way particles behave, how they move, how they interact. Yet hidden within its equations is something unsettling. Time itself often seems to disappear. At the quantum level, the very thing that feels so essential to us, the forward flow of seconds, the distinction between past, present, and future begins to blur. Think for a moment about the way quantum equations work. One of the central equations in quantum mechanics, known as the Schrödinger equation, describes the state of a quantum system. It tells us how probabilities evolve, how a wave function changes. But here is the strange part. This evolution does not always need time the way we imagine it. For certain quantum systems, the mathematics seems timeless. The equation does not speak of minutes or hours, but only of relationships between states. It is as though the fundamental language of reality cares more about how things relate to one another than about when they happen. This timelessness becomes even more striking when we consider the Wheeler-DeWitt equation, an equation proposed in attempts to merge quantum mechanics with Einstein's general relativity. This equation, which tries to describe the universe as a whole, contains no time variable at all. It is frozen, static, describing the entire universe in one timeless block. If this equation is correct, then time as we know it is not fundamental. It does not appear in the deepest description of reality. Instead, time must emerge from something else. But how could that be? How can time, the very fabric through which we experience everything, not exist at the most fundamental level? Imagine a movie reel. On the reel, all the frames already exist. The beginning, the middle, the end, they are all there. The film itself does not move. Yet when you project it, when you view the frames one after another, you perceive motion. You perceive the unfolding of a story. Some physicists believe time works in a similar way. The universe, at its most basic level, may be like the film strip, with everything already laid out. Our conscious perception, and the processes that generate entropy, create the illusion that frames are passing, that time is flowing. In the quantum world, we also encounter particles that appear to defy our normal sense of sequence. A photon of light might travel from one point to another, and its path can only be described as a superposition of possibilities until it is observed. Some interpretations even suggest that particles explore all possible paths at once, including paths that move backward in time as well as forward. Only when an interaction happens, what physicists call a measurement, does the situation crystallize into a definite outcome. If you think about this carefully, it means that time, in the quantum world, is not a simple arrow moving in one direction. It is a web of possibilities, a shimmering haze where past and future are not yet distinguished. Quantum entanglement deepens this mystery further. When two particles are entangled, their states become linked, no matter how far apart they are. Measure one, and the other instantly takes on a corresponding value. This happens even if the particles are separated by vast distances, faster than light could ever travel. What does this say about time? It suggests that the relationship between events may not depend on when they occur, but only that they are connected. Entanglement seems to live outside of our normal sense of past and future, as if the universe itself does not care about the order in which things happen, only that they are part of the same whole. Some thinkers propose that time itself emerges from entanglement. The idea is that the correlations between quantum systems create the illusion of a sequence. As systems interact and information spreads, what we experience as time is simply the unfolding of connections. In this view, time is not a river flowing forward, but a pattern of relationships knitting themselves into greater complexity. Our sense of before and after may be nothing more than the perspective of observers embedded in this web. Another perspective comes from the idea of quantum decoherence, the process by which quantum systems lose their strangeness and appear classical. The way we normally see the world. When a quantum system interacts with its environment, its superposition of possibilities collapses into one outcome. It is in this transition that many physicists believe time emerges. Before decoherence, the system is timeless, existing in many states at once. After decoherence, we perceive one outcome, one history. Time, then, may be something that crystallizes when the quantum world meets the classical one. This strangeness echoes into the field of cosmology, where scientists try to understand the universe at its very beginning. At the Big Bang, when everything was compressed into a singularity, time as we know it may not have existed. Quantum physics suggests that before the expansion began, the concept of time might have been meaningless. Only as the universe grew, as entropy began to increase, did time emerge. If this is true, then time is not an eternal backdrop stretching infinitely in both directions. It is a property of our expanding cosmos, born alongside space, emerging with the first sparks of creation. The timeless nature of quantum physics also raises profound philosophical questions. If time is not fundamental, then what does it mean to say that something exists or does not exist? Our language is steeped in temporal concepts. We speak of beginnings and endings, of past events and future possibilities. But if the universe at its core is timeless, then existence might be something different altogether, something that transcends the very categories of before and after. Some physicists and philosophers argue that reality may be a kind of timeless whole, an eternal structure in which all events coexist. Our experience of flowing through it is like moving through the frames of the film, guided by entropy and consciousness. And here we find another deep connection: consciousness itself. What role does the mind play in this question of time? Some interpretations of quantum mechanics, particularly those emphasizing the role of the observer, suggest that consciousness is not just a passive witness, but an active participant in shaping reality. If observation is necessary to collapse possibilities into outcomes, then perhaps our awareness is intimately tied to the creation of time. Without observers, without minds to string events into a sequence, maybe there is no time at all, only timeless quantum reality. This does not mean we create time in a trivial way, but that our participation in the universe is woven into its very fabric, inseparable from the way time appears. Others take a different view, arguing that time is real but emergent, like temperature. Temperature is not a property of a single particle, but of many particles together, moving and interacting. In the same way, time might not exist at the level of fundamental physics, but emerges when many systems come together in complex patterns. This perspective suggests that time is both real and unreal. It is not written into the core equations, but it becomes unavoidable when we look at the world as a whole. It is an emergent truth, like the warmth of a fire or the solidity of a rock. The paradox of quantum timelessness is that even though the mathematics suggests time does not exist, fundamentally, our lives are steeped in it. We measure it, we feel it, we grow older in its flow. Yet, beneath this experience lies a reality where time might be nothing more than a shadow of deeper relationships, a useful concept that emerges from the interplay of entanglement, decoherence, and cosmic expansion. At last, we arrive at the central question, the one that has been lingering behind every discussion of relativity, entropy, and quantum physics. Does the universe know what time it is? At first, the question might sound almost playful, as if we are asking whether the cosmos itself owns a watch or keeps track of seconds like we do. But beneath the surface, this question is profoundly serious, because it touches on whether time is something real and fundamental, or whether it is an illusion that exists only in the minds of observers like us. To explore this, we must carefully reflect on all the layers of science and philosophy that lead us here. Imagine asking the universe itself, what time is it right now? What would it say? In our everyday experience, time is the simplest of concepts. We look at a clock, we measure durations, we agree that this moment is different from the one that came before. But physics tells us that this everyday simplicity dissolves when you look more deeply. According to relativity, there is no universal now. What you call the present is not the same for someone moving quickly through space, or for someone near the edge of a black hole. The universe, in Einstein's view, does not contain a single shared clock that ticks for all. Instead, each observer carries their own measure of time, written into the fabric of spacetime as a personal path. So if you ask the universe what time it is, the answer might depend entirely on where you are standing, how you are moving, and what you are experiencing. This leads us to the idea of the block universe, where past, present, and future all exist together as part of one vast structure. In this picture, the universe does not need to know the time, because all of time is already there. Every moment, from the birth of the stars to the far future, where galaxies drift apart, exists in equal reality. Our sense of moving from one moment to another is not the movement of the universe, but the movement of consciousness within it. The universe is not ticking forward. It is simply existing timelessly, with all of its moments laid out like pages of a book. To ask the block universe what time it is like asking the entire book what page it is on. The book contains all the pages at once. The page you are reading now is simply your perspective, not the universe's. But then we encounter the counterforce of entropy, the arrow of time that seems to drive everything forward. Entropy gives us a sense of direction, from past to future, from order to disorder. It is why we remember yesterday but not tomorrow, why glasses shatter but never reassemble, why we grow older and never younger. If the block universe is true, then entropy is the pattern that makes one part of the block feel like it is before and another part after. Entropy is not a universal clock, but it gives the illusion of time's passage, and it is this illusion that defines our lives. In this sense, the universe might not know the time, but it carries within it the gradients of entropy that create the appearance of flow. The universe does not wear a watch, but it does carry the scars of increasing disorder, and from those scars, we read the story of time. Quantum physics complicates the matter further. At the deepest level, the equations describing the universe often leave no place for time at all. The Wheeler-DeWitt equation, which attempts to unify relativity and quantum theory, does not include time as a variable. It describes the universe in a kind of eternal stillness. Yet here we are, in a world where time seems inescapable. This suggests that time is not fundamental, but emergent. Just as temperature is not a property of a single particle, but of many particles moving together, Time may not exist at the microscopic level, but may emerge when countless quantum systems interact. If that is the case, then the universe does not know the time in the way we think of it. It does not keep a master schedule. Instead, time arises as a byproduct of the interactions and entanglements of its parts. But what if time is not only emergent, but also relational? Some physicists propose that time does not exist independently at all, but only as a relationship between events. To say that one thing happened before another is not to point to a universal clock, but simply to describe the order of events relative to each other. In this picture, asking the universe what time it is makes no sense. Time is not a global quantity that can be measured everywhere at once, but a local pattern of relationships. The universe does not keep track of seconds, minutes, or hours. It only contains events, woven together by their connections. What we call time is our attempt to map those connections into a sequence we can understand. And then there is the human element. Our minds are deeply tied to time. Memory chains together experiences, and anticipation projects us into the future. Our entire identity is a thread spun between what has been and what will be. We feel time because of the way our consciousness processes change, layering perception into narrative. Without this narrative, the universe might be timeless. With it, time feels like the most fundamental reality of all. Perhaps the universe itself does not know the time, but we do, and our knowing is part of what the universe is. After all, we are not separate from the cosmos. Our brains, our thoughts, our very awareness of time are products of cosmic processes, shaped by the same laws that govern galaxies and particles. When we ask whether the universe knows the time, maybe we are really asking whether our own experience of time is an echo of something deeper. There is also the question of the beginning. If time emerged at the Big Bang, then the universe as we know it has only ever existed with time woven into it. To ask what time it was before the Big Bang may be meaningless, because there was no before. Time was born with the cosmos, and it has been unfolding ever since. Yet even here, physics reminds us that the question is slippery. At the smallest scales, near the origin of the universe, time may dissolve into a haze of quantum possibilities, where the distinction between past and future is not yet fixed. So does the universe know the time? Or is it still unfolding from timeless origins, creating time moment by moment as it expands? Philosophers have long debated whether time is something that exists independently or whether it is simply a human construct. Newton believed in absolute time, a universal clock that ticks regardless of anything else. Einstein shattered that view, showing that time is woven into space, relative to motion and gravity. Quantum physics goes further, suggesting that time might not exist fundamentally at all. These views leave us with a strange possibility. The universe may not know the time because there may not be a single time to know. Time may only exist within the experiences of beings like us, arising from entropy, from quantum entanglement, from the patterns of our consciousness. And yet, even if the universe does not know the time in a literal sense, there is something profound about the fact that we do. The ability to ask this question, to wonder whether the universe is aware of its own clock, is itself a reflection of the cosmos becoming aware of itself. Through us, the universe gains a kind of temporal awareness. Through our memories and our measurements, the cosmos looks at itself and says, "This was then, this is now, and that will be." We may be the mechanism through which the universe knows time, not as a number on a clock, but as the lived experience of change. So now, after our long journey through relativity, entropy, quantum physics, and philosophy, we return to the question we began with: does the universe know what time it is? The deeper we explored, the clearer it became that this question does not have a single, simple answer. Time, as we live it, feels absolute and undeniable. We measure it, we rely on it, and our lives are shaped by its flow. Yet physics whispers to us that time may not be as fundamental as we think. Relativity tells us there is no universal now. The block universe suggests that all of time already exists. Entropy gives us the arrow of change, but may only create the illusion of flow. And quantum physics hints that, at the most basic level, time might not even exist at all, but instead emerge from the way the universe's parts interact. Perhaps the truth is that the universe itself does not keep a clock, but within us, time becomes real. Our minds, our memories, our awareness all are built around the passage of time. In asking the universe if it knows what time it is, maybe what we are really discovering is that we are the universe knowing time. Through us, the cosmos gains its sense of before and after, of story, a history, and of possibility. Without us, time may be just a pattern woven into the structure of existence. With us, it becomes an experience, a narrative, and a mystery we carry forward. And so, the question is not only about the universe, but about us. Time is not simply something we observe, it is something we live, something we embody. Whether or not the universe knows the time, we do. And in knowing, we are part of the great unfolding mystery of the cosmos itself.